Chapter 29, Section 2, Interactive Reader, pages 463 through 466, worth 11 points. The Sun, solar activity. Key ideas. As you read this section, keep these questions in mind. How are sunspots related to powerful magnetic fields on the Sun? What are the differences between prominences, solar flares, and coronal mass ejections? How can the solar wind cause auroras on Earth? Page 463. How is the area of the convective zone beneath the sunspot different from the area beneath granulation? Why do the sun's gases move? Highlight. The gases in the sun are constantly moving. Energy from the core pushes the gases outward. Continue. Highlight. The force of the gravity pulls them inward. Highlight. The sun's rotation also causes the gases to move. Continue highlighting. Because the sun is a sphere, each point on the sun rotates at a different speed. For example, places close to the highlight sun's equator rotate once every 25.3 Earth days. Continue highlighting. Places near the poles take 33 days to rotate once. Continue highlighting. On average, the sun rotates once every 27 days. What are sunspots? Highlight. The movement of gases forms magnetic fields in the sun. Continue highlighting. These fields slow down convection in parts of the convective zone. Continue highlighting. That means that less energy is transferred from the core to those parts of the photosphere. Continue highlighting. Therefore, those areas are cooler than other areas of the photosphere. Continue highlighting. These cooler areas are called sunspots. Sunspots appear darker than the photosphere around them. The rest of the photosphere has a grainy appearance called highlight granulation. Next to the picture, the diameter of this sunspot is larger than the Earth's diameter. The area around the sunspot shows granulation. How is the area of the convective zone beneath the sunspot different than the area beneath the granulation? Answer. Convection has slowed down the movement. Convection has slowed down the movement. Less energy is transferred. Convection has slowed down the movement. Less energy is transferred, causing a cooler area. Causing a cooler area. Convection has slowed down the movement. Less energy is transferred, causing a cooler area. Page 464. What might scientists have observed about sunspots that led them to conclude that the sun rotates? When will the next high point in the sunspot cycle probably occur? What is a solar eruption? The sunspot cycle. Astronomers have studied sunspots for hundreds of years. Highlight. In fact, they discovered that the sun rotates by watching how sunspots move. Continue highlighting. Later, they discovered that the number and location of sunspots change in a cycle that lasts about 11 years. At the beginning of a sunspot cycle, the number of sunspots is very small. Slowly, more sunspots appear, especially in the area about halfway between the equator and the poles. The number of sunspots increases every year until there are more than 100 sunspots. Then, sunspots at higher latitudes slowly begin to disappear and new ones appear near the equator. Slowly, the number of sunspots decreases and the cycle begins again. Question 2. What might scientists have observed about sunspots that led them to conclude that the sun rotates? The sunspots are moving with the sun. The sunspots are moving with the sun. Question 3. When will the next high point in the sunspot cycle probably occur? The image, the graph in the center, the peak right in the middle, that was the year 91. Put 91 above the peak right in the middle. Which means that 11 years later, the peak on the right-hand side was 2002. Put 2002 above the peak on the right-hand side. Add 11 years to 2002 and put 2013 outside of the table on the right side. Add 11 more years. Put 2024 next to the table on the right-hand side. Your answer to question 3, when will the next high point in the sunspot cycle probably occur? 2024. 2024. What are solar eruptions? The sun's magnetic field can affect the solar activity cycle too. This cycle describes the increases and decreases in different types of solar activities, such as solar eruptions. Highlight: during a solar eruption, the sun lifts a lot of material above the photosphere and emits tiny particles. Prominences, solar flares, and coronal mass ejections are 3 examples of solar eruptions. Highlight: during solar eruption, the sun lifts a lot of material above the photosphere and emits particles. Continue highlighting into prominences, solar flares, and coronal mass ejections are 3 examples of solar eruptions. Question 4, what is a solar eruption? The sun lifting material above the photosphere and emitting particles. The photosphere and emitting particles. Again, it is the sun lifting material above the photosphere and emitting particles. Prominences. Highlight: prominences are huge clouds of glowing gas that form arches above the sun's surface. The shape of the sun's magnetic field makes prominences form huge arches. Highlight: the prominences bend to follow the sun's magnetic field. Page 465. What is a solar flare? How does a geomagnetic storm form? Solar flares. Highlight: solar flares are the most violent of all solar eruptions. Continue highlighting. A solar flare is a sudden eruption of electrons, protons, or other electrically charged particles. Scientists do not know what causes solar flares. However, they do know that, highlight, solar flares release the energy that is stored in a sunspot's magnetic field. Solar flares rarely last longer than 1 area. Highlight: during a peak in the sunspot cycle, 5 to 10 solar flares may happen every day. Next to the picture, coronal loops like this one sometimes form during solar flares. A coronal loop can stretch more than 500,000 kilometers above the sun's surface. What is a solar flare? Answer, a sudden eruption of electrons, protons, or other charged particles. Of electrons, protons, or other charged particles. Again, it is a sudden eruption of electrons, protons, or other charged particles. Coronal mass ejections. Highlight. Sometimes the sun can throw off parts of the corona. Continue highlighting. This is called a coronal mass ejection. Continue highlighting. Particles from a coronal mass ejection fly into space and can hit Earth's magnetosphere. Continue highlighting. Earth's magnetosphere is the area around the Earth that contains a magnetic field. Continue highlighting. A coronal mass ejection can disturb Earth's magnetic field. Continue highlighting. This disturbance is called a geomagnetic storm. Question 6. How does a geomagnetic storm form? Answer, a coronal mass ejection happens. A coronal mass ejection happens. The material hits Earth's magnetosphere. The material hits Earth's magnetosphere. Again, a coronal mass ejection happens. The material hits Earth's magnetosphere. Highlight. Geomagnetic storms can interfere with radio communications on Earth. Continue highlighting. They can also damage satellites or cause blackouts. A few small geomagnetic storms happen each month. Severe geomagnetic storms happen, on average, less than once a year. What are auroras? Highlight. When the solar wind interacts with Earth's magnetosphere, auroras can form. Continue highlighting. Auroras are bands of colored light in the sky. Continue highlighting. The particles in the solar wind are attracted to Earth's magnetic poles. When the particles interact with the magnetosphere, they give off light. Highlight. Most auroras form near the north or south magnetic poles. Auroras can be called, highlight, aurora borealis, northern lights, or aurora australis, southern lights. Page 466. Why are sunspots cooler than other areas of the photosphere? Describe one difference between prominences and solar flares. Why are most auroras seen near the magnetic poles? How are sunspots related to solar flares? Describe two examples of how solar activity can affect people on Earth. Question 1, answer can be found on page 463. The sun's magnetic field slows down convection. The sun's magnetic field slows down convection in certain areas. In certain areas. Less energy is passed from the core. Less energy is passed from the core. Causing the areas to be cooler. Causing the areas to be cooler. Again, the sun's magnetic field slows down convection in certain areas. less energy is passed from the core, causing the areas to be cooler. Question number 2. Answers can be found on page 464 and 465. Prominences are loops of material. Prominences are loops of material. Flares release materials to the solar system. Flares release materials to the solar system. Again, prominences are loops of material. Flares release materials to the solar system. Question 3, answer can be found on page 465. The particles in a solar wind are attracted to Earth's magnetic poles. Earth's magnetic poles. Again, the particles in a solar wind are attracted to Earth's magnetic poles. Question number 4, page 465. During peak sunspot activity, there are more solar flares. There are more solar flares. During peak sunspot activity, there are more solar flares. Question number 5, also on page 465. Interfere with radio. Damage satellites. Cause blackouts. Any of those would work. Any 2 of those would work. Interfere with radio, damage satellites, cause blackouts.